Fosca est connecté? Est-ce que Fosca est connecté? D'accord. Okay. Thank you for coming. It is my pleasure to introduce Fosca Giannotti, who, so she's a professor of computer science at the Scuola Normale Superiore, I hope I pronounce it well, at Pisa. She's where she leads the laboratory on knowledge discovery and data mining. She's a renowned colleague. She's been featured as one of 19 inspiring women in AI, big data, and data science. And she's currently the principal investigator of an ERC project called XAI on science and technology for the explanation of AI decision-making, which is the topic of the talk that she kindly accepted to present us today. So thank you, Fosca.
Shall I share the video, the screen?
Yes, please.
Okay, so
perfect.
Can you see everything? So let me check. Okay, it works. Okay, so thanks for inviting me to this this meeting. Now, I think it's very important that we establish more contact that is possible among the various initiatives on artificial intelligence all over Europe. So I'm particularly proud of being here. So my talk, as you said, so I titled Explainable Machine Learning for Trustworthy AI, but indeed will be focused on the results, current status of the ERC project. So I will try to give you a bit of motivations that are behind the arena of explainable AI, various forms of explanations that we are aiming to produce out of machine learning models. And then I will focus on some of the methods, some user studies that we have done. And also what are the next challenges that the people working on this area should face, in particular explanation as a human-machine collaborations. So motivations are now, I think, there are sort of manifesto of the motivations behind the explainable artificial intelligence. It's the problem is that how much can we trust AI? So, and there are here 4 examples which are particularly famous in, so when the lack of trust come from the bias that we may have on the data. There are, so the first example of ASCII dogs and wolves, the system that was capable of recognize, that was used by the work, the famous, seminal work of Ribeiro in KDD 2016, where so a system trained for discriminating images from husky dogs and wolves failed in one image. This is the image on which it failed, and then the explanation behind that was that there was the system used the machine learning methods that was trained on such images as most relevant variables used the snow in the background. So this is to message here. So from one, a system that we cannot trust if the motivation behind what has the system learned is just the snow. This is a bias which was on the data, was not really learning any concept related to the wolf and the husky dogs. So the images on which it was trained were unbalanced with respect to having the snow behind. Actually, the machine learning methods was particularly efficient in discovery. That was the most fast and significant feature, which was just the snow, to discriminate. And this, of course, is not something that we can. It is not really helpful for a recommendation. So that is an information which is not related to the major concept that the humans are recognizing in that image. Or the other example is the system trained for predicting the risk of death from pneumonia, that was giving a very low risk to a patient which had asthma. And then, so again, looking behind, the explanation was that the people with asthma indeed were under the other medications. So that's why the system was in the historical data, in the historical record, the risk was lower. So the system learned a lower risk for that kind of patient. And then, of course, the very famous compass examples that was discovered to be, let's say, a little bit biased against the Afro-American race, providing a very higher risk for humans in that with Afro-American race, for risk of reiterate crimes. So that was discovered by the ProPublica journalist and became a sort of the reference examples for demonstrating how much untrustable were the AI system. So this is exactly. So all the discussion that started from these examples activated a long debate, and actually Europe was very ahead in this debate, including this the relevance of having explanation in AI system as a sort of a right of explanation in the case of a decision, this automatic decision, which were decision involving humans that were supported by automatic system. And GDPR, there is Article 22 that explicitly says that the humans under object of that decisions should be to them should be produced an explanation of the logic behind that decision. So the long discussion. So GDPR, which was enforced in 2018, was inserted this argument of an explanation at the end of a couple of years of discussion. Then there has been more activity in Europe with a high-level expert group, recommendation and requirements, and then became part of the current proposal of the AI Act, where in those AI systems that wish to be put in service in Europe, that are considered high risk, and they are mostly those which are related to decision concerning humans. Those should have should be ensured the appropriate degree of transparency and provide users with information and capabilities and limitation of the system how to use this. So this is also the legal and ethical requirements for this. So, but indeed, the problem which is behind all the stories that so we want to have AI we want an AI-based decision-making system supporting decision-making in high-stakes scenario that have to be very trustable. Criminal justice, finance, healthcare, where decisions are taken on humans, and where the decision maker is in front of situation that he has to do something to take a decision on the future of a person that can be released or not by the prisons, a future of providing or not a credit. The decision makers normally has to take this decision in a context with uncertainty. He doesn't know the futures, but he has to take the decision using a lot of information, which are part of its own background of knowledge. And of course, the AI system may help this decision maker because, of course, the amplifying the capacity of learning from enormous quantity of data which are nowadays available. So we cannot lose this opportunity of gaining trust and providing help to decision makers, even in this particularly high-stakes scenario. So there are two possible situations that may happen here. Or the decision makers, which may be the expert, the judges, maybe the bank office or the others, or the decision maker does not trust the AI system, and so take the decision with other form of knowledge, or it is over relies on the system, and in some sense does not use any critical thinking by its own. So we are in a sort of explainable AI has to help in between this extreme. So do not trust AI or trust too much AI. So you cannot we cannot go in a direction of a society where humans demand their decision to an algorithm. No, we have to stay in a place where the automatic decision support to the decision, it's helpful. So, and the AI, it's so we consider we are this is the path that we are taking in the project. We see explainable artificial intelligence as a crucial aspect for preserving people's autonomy of actions. So, being in a sort of between these two extremes of trust with respect the recommended decision by the automatic system. So the problem is difficult because it is not clear what is an explanation. So it is an old question, and all the philosophical questions debated, strongly debated, because depending by an explanation may be a story, an explanation may be a model, maybe an example, an explanation may be by some model, some mathematical representation of something. This strongly depends. So what is more effective for habilitating the cognitive process of the users is something that is really what is the challenging part of this part. Now, if we another topic, another argument which is on the arena so far, it's explanation and interpretation. What I like to the definition from Merriam-Webster dictionary that see interpretation as the means is the action towards meant to give the meaning or to explain. So to interpret is the actions for producing it's the ability to explain. So at the end, the explanation, it's a noun, it's the object that we are capable of producing out of interpretation. But as I was saying, so the explanation depends by the context, and in particular by the context of our users. So the user so what is a good explanation for whom? It's the difficulty, or one of the difficulties of this area. So the user maybe wants to know, am I treated fairly? Or the engineers want to know, is my system working as designed? The regulator, is it compliant? So that means that that's why the field is so wide. There are those three different type of users to which we want to provide information, explanation extracted in some form by the machine learning. So explainable AI is about producing technique that explain human understandable terms, the reasoning behind the black box. And the area, it's very wide, and it is not new, as we are. So there has been an hype recently in the last 5 years of this area, but it's there since many years. And any different field of artificial intelligence has done a lot of effort in producing explanation exactly with this idea of which kind of explanation should I provide to whom. Okay, so here are examples. I will go through a few examples of explanations. So one kind of explanations which are being studied so far are feature properties and relevance in the space of the data that we have. So we may have a feature relevance in the case of tabular data, maybe simply a linear model that give us the weight to which each features can contribute. Can look to the random forest part. What is the way? This is a linear model where and the weight, the numbers that we see on the weight, we see the contribution of each feature to that the explanation. Or again, feature relevance in the case of image is what we call saliency maps, where essentially each pixel, it is we can see what is the contribution to that particular prediction of each pixel. For example, we see so this image, the bird, the image has been predicted to be a junco bird. And then you can see there are different methods which produces saliency maps, so feature relevance. And then each of them has a different way, more useful or less useful, to highlight which are the pixel which particularly contributed to that prediction. In the case of text, the explanation is highlighting, it's aimed at highlighting which portion, which words which sentences of the text have been contributed to a specific prediction. It's a recommendation of movie. So, and these are the tests describing the definition. It's the same text describing the movie. There are two different users, but different portion of the test as contributed for the two different prediction. Or might be prototypes. So this has been a junco bird because in my training set or somewhere I find similar by part similar images which are similar to the portion of the portion of images of these images so far. And by this prototype are labeled, we can say, unlabeled as a junco bird. So because of this similar the similar prototype are labeled my training set Gianco Bird, that's the reason why I predicted Gianco Bird. Or explanation as narrative, even more complex. So this image has been predicted to be a Western grape, and then the narrative which has been constructed in this case is a combination, is a description, it's a definition, maybe a visual explanation. And in this case, that means that we have been capable of constructing this narrative, adding to this prediction some extra knowledge. You might imagine might be a knowledge graph or Wikipedia or something else for which we might add this further information. Or explanation may be counterfactual. Counterfactual is another important form of explanation where essentially you habilitate a sort of contrastative reasoning in your users. So saying that why, but also what can be changed. So you obtained this classification, this outcome, but what you can do for changing and obtaining a different outcome. So your loan application has been rejected because these features, the following features were too high, the following features were too low. What can be changed? Not all of them. Of course, you cannot change everything. And the game here is trying to propose a sort of minimal change that you can do to your, so a minimal feasible change that you could do to this, to the instance under study, such that so you to obtain such that these features, this instance can obtain a different outcome. So now we are in the, so those are the type of explanations that are around, but so the entire status is that we are now in the point that while a lot of effort has been done in producing explanations out of machine learning methods, we still have to do something else. So we have to move from, the idea is that to move from a pipeline of machine learning that simply learn the process and then the machine learning process produce a learned functions, which is then put into the service, an automatic system, a decision process. And then this learned functions simply says a recommendation without any further information, and give the raised untrust because of a lot of doubts. Why you did that? Why not something else? Why do you succeed? What else? So to another scenario where the pipeline for machine learning, the XI supported pipeline, will be a new machine learning process which produces also explainable models, which a box which is composed by explainable model and explainable interface that is capable of producing a different form of interaction. I understand why not. I know when you succeed. I know when you erred. I know when you fail. I know when I trust you. So changing the paradigm. This is also you know that there is also a big project in US, the DARPA project on XI. This is also the vision, the current vision of that project, to which I agree very, very much. So essentially, what on explainable model means that we have to develop a range of new or modified machine learning techniques to produce more explainable models. But also we have to integrate the state of art of human-computer interaction with new principle and strategy technique to generate effective explanations. So now human-computer interaction and explainable models have to tie, and also take into consideration which is all the science on the cognitive cognitive part, so having a better understanding of the cognitive process of the end users. So, and also taking advantage of all the results and achievement of the psychology of explanation, using also psychological theories of explanation to develop a computational theory. So now, after these premises, I let you to see what is current status of the project that we are running since 2018, with this idea that the AI as a basic building brick for preserving and expanding human autonomy and helping human to make a better decision. So the model that I like to share is that that we would like to achieve in this new pipeline of XI empowered machine learning pipeline is the Dr. House model. So Dr. House is a very smart agent that interacts with other very smart agents. Those are producing new challenge, new hypotheses, and then, but at the very end, the responsible for the final outcome, it's the Dr. House. Dr. House is the human in our vision. So what we'd like to habilitate is an explanation as a human-machine conversation where there are several interactions between the machine learning models that can produce explanation in different forms, as a roots, as a natural language, as a narrative, but it can also be contrasted, asking also inspection of what is the status of the training set, and also being capable of reactivating some other different machine learning process. So here the example is that my machine learning classifier thinks to the compass examples. So predict that I have a high risk of recidivism. Can be the why part can be expressed both in terms of logic rules or in terms of a natural language. Then the human asks, okay, which training examples are most similar in the instance influencing the outcome and which not? So exemplar and counter-exemplars, similar instances and dissimilar instances. That can be part of the training set or synthetic data which are coherent with the decision boundary of where the machine learning methods has learned. Then what happens if you don't consider that she is young and the recidivist? So what if I remove some feature? It's still coherent. Then the machine learning classifier can predict, still a high risk of recidivism because she is blue. So in this case, you can see how much the one of the features was particularly relevant for that decision. And then, of course, you can go home. Okay, let me see why. Okay, so the way we are studying in the ERC project, we have different research lines. One is the algorithms and models for explainable machine learning. So in the area, new explainable machine learning models, language for expressing the explanations in terms of logic roots, but also statistical causal interpretation. So there is a platform also that we are creating as a common space for researchers working in this area for explaining and comparing different methods. And then we have also a line for use cases, but use cases meant not necessarily case study for validating or validating what we have, but use case where we involve humans, with the objective of understanding the utility, the impact of our decision. We are trying to set up a methodology for trials where we can involve humans, collaborating with psychologists and to try to set up experiment with humans. And of course, there is another important part. This is so we know that explanations may conflict with privacy. So what is the impact? So what is the ethical and legal framework for explanation? It is useful for some of ethical issues, for fairness. For example, it is dramatically useful. It is dramatically useful also for explaining, for example, privacy risk, but may put in danger also the individual privacy. So there are all these conflict issues that are studied there as well. So I will concentrate mostly on because it's where we have more results so far, consolidated results on the algorithms and models, and then so there are two big categories of big families of explainable machine learning models. One is explanation by design, where essentially, so the goal, given the training set, how to develop machine learning models, which are together with its explanation. So they're capable of during the training phase, also of recording the appropriate traces to make it easy, natively easy to generate the explanation. Or the other family, which is the black box problem. So where essentially, so we stay with the decision. We stay with the black box, which is trained on decision record, but the black box, it's inscrutable. We cannot open it, and we try to reconstruct an explanation out of simple interacting with the black box. This is called also a post-hoc explanation. So the black box is there. You cannot change it, but you can produce a different system which produces explanation. Okay, some basic. So this is also another way to see the taxonomy of the explanation models. So the by design method essentially during the training phase try to arrive by the training during this training phase to learn a white box directly, and then we will use the white box learned there. While in the post-hoc explanations, you create a new subsystem, a new piece of software and explanators that we call explanators that is capable of producing explanations, but it can the way it produces this explanation, it's by an interaction with the explanators. So the explanations are data dependent. So there are forms of explanation that are suitable for tabular data, rule-based, feature importance, prototypes, counterfactual. Other are suitable for images, saliency map, concept attribution, prototypes, and then text, sentence highlight, attention-based, prototype, and counterexamples. Those are the type of explanations. There are also desiderata. So here, I skipped this image because simply repeating the same, showing that a family of explanators are, so on images, the focus is so saliency map means find a way to highlight the pixel, or to highlight a different portion of images as Lime does, or Sharp is another explanators that highlight the group of features, and then explanation by example. So you produce images of ships. So with text and examples. So cooking with my stepfather, and the outcome of the recommender system is a sentiment. The sentiment for this test is positive. And then Lime, it's one of the explanators that we'll see very, very, very short. Highlight some keywords. Sharp, again, highlight the keywords, but the rendering. So give you the contribution, positive or negative contribution of that keywords to the positive outcome. And explanation by examples show you different sentences which were labeled positive. Jogging with my mom, shopping with my best beast. Those are positive examples that should explain why this text was considered having a positive sentiment. There are properties that there are desiderata from this explanation that we obtain. That so the explanator should behave as the black model, should provide similar, if it not giving opposite outcome with respect to the black box, different outcome with respect to the black box. So given the same input several times, the explanation should remain the same. We will see the reason for this. And then for similar record, we should have similar explanations. So this property now, so you'll understand better once we go deeper in the various proposals, because indeed they might behave. So they might be very significant for observing the behavior of these explanators. So now the first focus that I do is on the post-hoc explainers, and then I will focus on those which I've designed in this XI project, but they are also representative of research lines which are current in literature. Unfortunately, we are not the only ones doing this. So we have done this post-hoc local explainer, which is named LORE, which is a rule-based factual and counterfactual explanations. So we have in the post-hoc we have 4 different explanators. One is LORE based on ontology. One is Abele based on latent space. I will, and one is LORE for time series. So it's a families of algorithms which all share this idea of LORE, which is, and I will go deep in this in LORE and the others. So LORE is a local rule-based explanation. What does it mean to be local explanators? Essentially, it's agnostic with respect to any black box. And essentially, it doesn't want to reconstruct, given the idea of the post-hoc explainers is that what they are doing, all of them, are doing a sort of re-engineering of the black box. They can audit the black box, asking a lot of questions. They have a lot of new examples, and from the input and output, the collection of input and output of the black box, they try to reconstruct what is the function which has been being learned which uses the black boxes. What is the functions that uses the black box? the local explainer don't pretend to reconstruct a global model to be capable of answering to all, to reconstruct the entire decision space of the black box, but they try to do it locally. In this example, here we have the space of the training set. The decision border is the one surrounding the dividing, discriminating the two colors. So if we have a very efficient black box, probably has learned very well how to, so this border around which separate, well, of course, also the black box may do mistakes, of course, but reconstructing a global model, a post hoc explainer, global, will try to reconstruct the entire separation between the two and use such a separation that he has learned to mimic the behavior of the black box. Here we stay with the local. That means that what we do, we try to, given the instance to be explained, those family of methods, post hoc local, try to generate a neighborhood around the instance to be explained, doing some perturbation, generating synthetic data, doing perturbation, and then for each of the instance which has been generated as a neighborhood, they ask to the black box to label. Still, we have enough points which are labeled positive or negative if it's a binary classification. Now we are in a condition to have a very small training set, and then we can use this small training set for train a transparent mode. We know there are some transparent model like decision trees or regression trees, which we can very easily from these models produce explanations. So out of this neighborhood, we construct a decision tree. And the various methods depends the different methods in this area. They vary for the kind of algorithm that they use for generating the neighborhood. And once they have generated the neighborhood, in this case, this is using a genetic, here we use a genetic algorithm, then we can construct a decision tree out of this, a decision tree that tries to reconstruct locally this border. You see that the black line here has obtained a sort of separation. The idea behind all this method, this local, is that maybe to reconstruct the entire decision border may be very complex, but locally it may be easier. And out of this once you have constructed this decision tree, you are capable of producing rules and also counter rules. Counter rules in the form of counterfactuals in the form of rules simply visiting the decision tree and try to go backward in the visit and do the minimal changes that you can do visiting backward the decision tree for generating a counterfactual. This is an intentional, even the counterfactual is an intentional representation. It's a rule. So here the rule is that this is the instance to be explained, X, which is the age 22, income 800, job clerk. So the motivation, and it was denied. The reason, the why, it's because the age was less than 25, that learned by our local decision tree. The job was a clerk. The income was less than 100. What he has to do for changing? It's going up in the decision tree. So the income was greater than 900, and job remaining the other feature the same. It was it was granted. Or another counterfactual might be, you can be even younger, between 17 and 25. I'm going up and going down on the other side of the decision tree, where there is the age as a condition, and then construct factual counterfactual. Just to let you know, Lime, that was the first adopting this, proposing in the community this local explanations. He was using for generating the neighborhood, was using a random neighborhood, which is capable of creating a very wide area of examples. And then he constructed a lasso out of this, a regression model out of this. While Lore, it creates, with using this genetic algorithm, uses a very close, generate a neighborhood very close to the instance to be explained. So the good news is that now, if you compare on fidelity and on the various data sets, really you cannot see that what is there is a unique winner, because strongly depends where is our instance to be explained with respect the decision border. So if the instance is very far away, in this case, it's much better the random neighborhood. If the instance it's very close to the neighborhood, it's much better the genetic algorithm. So just to see that the complexity behind these things. So counterfactual, I just say that it's really useful as a mechanism for activating a different cognitive process. So it is really a line which is very, very, very important. So here a little bit of comparison on the Compass data set of what we produce. There are several other proposals in literature. One is Anchor, which is an extension of Lime. Lime at the beginning was just this is the on the right side you can see the answer of Lime. Lime is as I was saying, it produces as an explanation a linear regressor, and then you see the contribution of the weight represent the contribution of each features. We with Lore we express rules, but also Anchor, which has been a further extension of Lore, produces rules. Now, to compare the rule produced is not that easy. But however, this is the thing. For example, Sharp, which is another explainer, simply says that age contributed to the negative outcome. Age was the major contribution to the negative outcome with 0.7. So okay, so we also added extended the Lore for a different domain. So there are domains where you might have further information. In particular, we experiment Lore in the case of a health domain where we have an ontology. So the way we generated the neighborhood, and the way that we generated the answer was driven by the ontology. The ontology, in this case, a health ontology. The case we have a sequential data. We want to do prediction. What will be next step? So we have the clinical history of patient, and in the case so both the neighborhood and also the decision tree are generated. One is generated using this ontology. It is on sequential data, and also the other characteristic is that the outcome of the classifier, in this case, Dr. I, which is one famous, quite famous black box used for some form of medicine to predict the next visit of the patient, what will be the next problem of the patient. So we explained the Dr. I using this ontology. So what you have, so you have several issues. Then there are the codes of the ontology at the visit, and then the decision rules. It is then transformed in using the language of the ontology in a more understandable way. But the novelty here is that even the neighborhood is generated using the ontology. It's not are synthetic data, but synthetic data which are meaningful with respect to the ontology. So the way we introduce the perturbation is ontology driven. Now there is another interesting thing. So, okay, so we asked ourselves, but what about now? We are on tabular data. We made things on tabular data, but if we move on image data, so the number of features, when the feature grows too much, maybe that it's not anymore useful. Even this local explanation with the decision trees. Generating the neighborhood, maybe moving a pixel by pixel on image, maybe not that efficient. So we had this idea. So I'm sure that all of you knows the adversarial autoencoder technology, where essentially we learn an identical. So we reduce we are capable of compressing the data in a reduced space, and we learn the function, encoder and decoder, a sort of identical function, but also we learn also the distribution of the data. So now image, that this is essentially what, so this is we encode, this is the in image that represented 0, we encoded the different space, and then the decoder give us the new X prime, which may be, which reconstruct the input. It's a synthetic X tilde. It's a synthetic, but it's the closest to the input. So how we use this idea? So essentially, the idea is that, okay, with images, why don't we simply go in the compress in the latent space? We compress in the latent space. And then for each element of the latent space, we generate the neighborhood in the latent space, and we then for each element of the neighborhood in the latent space, we label. We go back, thanks to the code function. We go back to the original space, ask the black box to label. So at the end, we have in the latent space a training set, which is in the domain of the latent space, but it is labeled thanks to the black box. Now we can construct a decision tree in the latent space that give us rules and counter rules. Of course, the problem is that so this decision tree and these rules will be, so we go back, we label with the decision. The problem is that these rules and these counterfactuals are in the space of the latent space, so are not really useful in terms of human understanding. We have simplified the problem because now, so the zero, so as being so we are capable of producing rules and counter rules with respect to the image, but not in a significant space. So we made a further step out of this, Now we are capable of producing what we produce here. We produce with rules and counter rules. We produce conditions on the lattice space, but those conditions can be used to select exemplars and counter exemplars. So now, as I said before, with adversarial encoding, I can produce also the distribution. Okay, now I am in the lattice space. I am capable of producing in the lattice space rules and counter rules, thanks to the fact that I'm capable of producing also going back to having the labels. But here, now I have the capacity, those rules and counter rules are a sort of filters in the lattice space for the elements that I can generate synthetically in this space. So I generate a set of synthetic elements in the lattice space, and then at the end, I have my decoding functions, which is capable of producing in the real space. So I start from zero, and with this complexity in the lattice space, emulating this again, capable of auditing the black box, I'm capable of producing exemplars and counterexamplers. So for zero, I have as exemplars those two images. For the image zero, not the number zero, for the image zero, I have two similar exemplars and two very different ones, and counterexamplers, not very different ones for very small. And I'm also capable of producing a small saliency map highlighting the positive and the negative. So I think I'm out of time. So I go this is very effective for the image. We tried on image medical images, and then this very complex image. So at the end, you'll have a system. You give the real image, and you have the prediction, and then you can produce exemplars and counter exemplars, and also highlighting the portion with the saliency maps, which have been useful for the explanations. So this can be done also with time series. I skip this because I want to talk and then you about something else, which is our experiment. Let me skip this. There is something that I want to say. So we have produced several other methods, also local to global, but there is something that it's very important that I want to share with this community, because we made an effort for involving the humans, studying the impact that may have explanation on this, on their decisions, and then essentially with this object to measure. So this trade-off between too little distrust and too much over reliance on the system. So ideally, explanation should help to the trust calibration process. So the nice thing that we set up with a prolific and experiment involving people working on healthcare and providing an expert on heart. So the topic was to predict the risk of an heart attack, cardiac attack. So the population provided by Profilic were experts of different level, some physicians, some nurses, and some others. So, and essentially what we want to try, it's so the question was that what are the chances that a patient will have an acute myocardial infarction in the near future? And then they have some of them, it was a blind experiment, some of them have a suggestion from the black box, some of them have a suggestion plus an explanation. So then we have to measure something that was a measure which is well known in psychology. So that's so we have to measure a quantitative and a qualitative. So weight of advice, which is simply the measure the degree of advice taking, which is correlated with the impact of trust in the system. And then some qualitative questions. What was your overall impression, the architecture? So the final outcome on the quantitative measure was that really having this explanation increased a lot, quite significant, the trust in the system, while having not, of course, there was also in the qualitative questions, there were wishes of improving and some system. But the next thing is that we decided this experiment with a psychologist. And so we, at beginning, as a computer scientist, our intention was to make this interface very, very beautiful, adding a lot of information for helping the user, a lot of, I'd say, visual stuff around. So, but the psychologists prefer to have a very simple things, removing all the visual things that we want to put there, keeping it very, very, I would say, nude. That was for us a surprise, because they want to remove as much as possible the intervention of other factors. At the end, one of the qualitative answers was the fact, okay, but can we add more visual stuff around? So they were, in some sense, were upset of how much poor was the interface, but they understood the fact that they could focus on the real stuff. So I conclude this with removing all the other stuff, because I think what is important now is what is next. What is next? Going to this human-machine conversation with these directions. So exploration as a synergistic human-machine collaboration, and it is important, this capacity of modeling, putting the focus on modeling the human decision-making process, and designing classifiers which are capable even to defer their decision, to ask to human second opinion, and vice versa, the humans that can ask a different opinion. So putting the user in control. So I know when you succeed, when you fail, when you trust us, and when you haven't. So this is now the focus of next research, our next research. Of course, we here need the human-computer interaction, people, and social science for sure. So I think that so the direction to help people make better decisions. So now we are in this second phase of the project. We are hiring, so we are plenty of open position in this 2023. So thanks for. I just told the half of the story, but I think it was even too much. Sorry for being late. Maybe I close the.
Thank you. Thank you, Fosca. Do we have questions here?
Thank you very much, Fosca, for the really interesting talk. My question is, in your last slide, you mentioned the human-machine interaction to get the explanation, and at the end, when a bias, here in this case it's a bias, but in other cases it just might be a bug or anything. Do you think that it's also within the realm of explainable AI to provide tools to fix the models?
Yeah, thanks for the question. This is a very important question. It's yeah, because as I was saying in the beginning, so there are two kinds of personas that we have in front that we are aiming to help with explainable one AI, and one is exactly the designer. One is the designer, and one of the goals should be understanding the kind of amplification that for bias or bad behaviors that the system can do. And this should open the door for fixing the bug. So there is a line which is interactive explainable AI, which is exactly meant, which goes in this direction to use also explainability during the training phase. So you are there, so you have the training, the learning, and the explainability, and you go back and forward. I think this is a very interesting line with the goal and the kind of measures that you should be there. So it should be related about the robustness of this, the final outcome. But definitely this is so interacting also with so activating a new learning or changing the learning. This is something that it's an option that at least in this in the phase of before the exploitation should be considered.
Thank you.
Hello, Ali speaking. Thank you for the presentation. You skipped the time series. I was wondering how you apply to time series. And I have one question about local explanation, if there's not a risk to miss some explanation by focusing on local explanation. Maybe there are some features or variables that you may ignore. And you mentioned that local explanation can be more visible. Is there any risk to miss some important information? And time series, please, also. Thank you.
Okay, time series, I just share again, but just not just for showing an image. I think it's one of our important work that we made. It's sorry for this. It uses the idea of okay, this is there is this work last local agnostic subsequence based. It's for classification of time series. Now we are working on prediction on the next. So classification means, is this time series? It's this sound a bell, or it's I don't know, a dog. So this is so, and essentially what we are doing there, this is the place where this encoding, working on the latent space is particularly relevant. But again, what we do is the same pipeline. In the first part, you see up is the first, we produce we produce in the latent space this labeling given by the black box. We construct a tree in the latent space for the time series, and generated a lot of exemplars time series and a lot of exemplars counter exemplars time series. So you generated the positive and negative instances, which are similar and dissimilar to the instance. And then once you have these examples, green are positive and red are negative, you can work on them like with, for example, with the technology that you have for time series, like shapelet, and also produce a decision tree in the space of the real space out of these examples and counter examples. So this is what we are doing. As far as the second questions, so you can have a look to this paper, and then we can interact furtherly. As far as the second question that you said, so there is the risk with the local explainers that we are missing something. So the current research on the area of local explainers it's trying to create a stable and robust local explainers. With, for example, what we do in Lore, we generated not only one decision tree, we generated plenty of decision trees, and we combine them. There is a question: are these exemplars disappeared? Let me see the chatbot. The chat. The question disappeared. I don't know. Okay, let's see on the very clever method to derive linguistic explanation from a numerical feature, but the statement is description and then causal. Yeah, it's not causal. James is asking if the
maybe can I ask a question? I don't know if the system allows me to do that. Yeah. Yes. So Fosca, thank you very much. That was very interesting. My comment was that LoRa is very clever. It's a method to derive a linguistic explanation from numerical features using a decision tree. And so it's a way of getting from one domain to the other. But the statement is descriptive rather than causal. It sort of says what happens around that region of the space, but it doesn't say why the decision boundary has that shape. And many times humans want to know why and not just what. Do you have any ideas about how a system could generate causal explanations? For example, is there a similar technique that we could use to generate linguistic interpretations from causal models? Maybe after the fact, after watching the black box.
Yeah.
Any ideas?
Thanks very much. For being capable of generating causal explanations, so you need one of the two things. One, you need the time in your training set for understanding. For first of all, you need to discuss to be able to capture causality. Or you do because there is time. So you need, for example, with the sequential data. So you can capture causality. For example, in the example of the second example where we use in the medical example, the information was a causal relation, but this is due to the fact that the training set, the data that we have, they were sequences. So the correlation it also represent that we learn also represent causality. And this is a direction that we are working on. Or you have so there are two different actions. You try to learn a causal graph, or because you have an extra information on you do. So there are methods now that are trying to discover causality in data. So and you have to combine the two things. So what about if you have a causal graph and then you are capable of producing a decision tree? So what would be a better explanation that takes in consideration both the two things? So this is at least my current understanding of the problem, which is very much interesting, because I agree causality is much more intuitive than what can be produced by decision tree that you can combine a different way.
Thanks.
I would like to ask a question, if you don't mind. Actually, so I'm personally very naive about all these questions. So I hope my question itself will not be naive. But if humans make biased decisions every day, and if it is based on a questionable bias, they will be very good at hiding the real reason, even maybe to themselves. So we can expect that people are very good at providing explanations which are not the real ones. Now, speaking about AI, we have now large language models which are extremely good, much better than human people now, at providing any convincing text about any unreasonable idea. So do we risk the situation where whatever the decision taken, we can be provided with a very convincing explanation, which is completely misleading? So if I try to iterate on that, the question is, how do you measure the validity of an explanation? Because you can probably, whatever the decision, provide millions of various explanations. So do you have a metric about explanations?
Yeah, there are several metrics on the explanation. One is the fidelity with the machine learning models. Of course, the fidelity means that we can, so the explanations try to explain what the system has learned. So in the system may have learned something which is not correct, but this is another story. So the system may be wrong and the explanations will learn. So we try to explain what the system has learned, highlighting possible problems, but not solving. So highlighting them. It's not, explanation is not capable of taking the remedy. It's an help for further remedies. But so what you said, it's even a wider question. So how can we produce narrative out of this explanation, and how this narrative can be coherent with the explanation? This is really, so far we have metrics for measuring the fidelity of the explanation for this form of explanation that I explained so far, which are rule-based exemplars. So we can measure the fidelity with the black box. We can, more difficult is to explain, is to measure the usability, the understandability of the explanation with respect to humans. Because sometimes you may use, for example, the fact that your explanation, it's if you want to quantify this, you can use something like minimum description length. So a shorter, a concise explanation may be easier to be understood from humans. Or so there are this tentative to provide metrics for measures these issues. But this is different of introducing an extra factor, which is language models. So the language models, if you use language models to transform logic rules produced by a decision tree in a narrative, and you need also to have some, of course, some measure for trusting this further step. And this is not yet the case, not if you use language model. We have some, and also this component should be part of the explanation. So in part of the explanation for a decision maker, you should be very transparent in all the steps. You should be very transparent on the property of the training set, on the property of the explanators, and also in this further transformation, if you want to use transform in a narrative. That is a very challenging interesting part now in this area, transforming in a narrative the explanation. So we know that the language models can be biased as well. So,
of course. Well, thank you very much. I believe we have to move on now. And, well, thank you.
So thanks for having me.
So now I believe we have a break, a small break. It will be only a 10 minutes break. And then we start again, so at 3 p.m. So in 10 minutes, anyway. Okay, sorry. 3:30, yes.